Okay, in this lecture, we're going to discuss Chapter 14's material, and this is going to be over fluids. All right, so the physics of fluids is going to be the basis of hydraulic engineering. Fluid is a substance that can flow like water or air and conform to a container. This occurs because fluids cannot sustain a shearing force, something that's tangential to the fluid surface. They can, however, provide a force that's perpendicular to the fluid surface. So if you think about a body of water, like a lake or something like that, there's no force that the fluid can exert that is going to be tangential, in other words, parallel to the fluid surface. It just doesn't happen. But all of the fluid can start exerting a force on things that are below it. So some materials like pitch can take a long time to conform to a container, but they're still considered to be fluids. And the essential identifier is that fluids do not have a crystalline structure. You're not going to see that. I mean, you see that in um, solids, and this is something that's not present in a fluid substance. So the density of a fluid is going to be defined as a change in mass over the change in volume. So in theory, the density at a point is the limit for an infinitesimal volume, but we are going to assume that a fluid sample is large relative to the atomic dimensions, in other words, the material that makes it up, and therefore has uniform density. So we're just going to say that the density is the same as the mass over the volume. Density is going to be considered to be a scalar quantity. In other words, there's no direction associated with it. In the units, generally, you're going to find are kilograms per meters cubed. The pressure of a fluid is going to be the force acting on an area, and it's going to be defined as the change in the force over the change in the area. So we could take the limit of this for an infinitesimal area, but if the force is uniform over a flat area A, we're going to write that the pressure is going to be the force divided by the area. And we can measure that with a sensor. Let's zoom in on this a little bit. So we've got our sensor here. We've got this. It's tied to a spring at the back end of it here. The fluid surrounding this particular sensor right here is going to have a force that's applied here onto this particular area. So that's how it's measured. So we're going to find empirically that for a fluid at rest, pressure has the same value at a point regardless of how the sensor is oriented. So that's why we consider static pressure to be scalar, even though force is a vector quantity. Only the magnitude of the force is going to be involved. The units are going to be the Pascal, which is defined as 1 Newton per meter squared. It can also be measured in atmospheres. It can also be measured in torr, which is the same as 1 millimeter of mercury. It can also be measured as the pound per square inch, or PSI. 1 atmosphere is going to be equal to 1.01 times 10 to the 5th pascals, which is equal to 760 torr, which is equal to 14.7 pounds per square inch. So hydrostatic pressures are those caused by fluids at rest. Air in the atmosphere, water in the tank. So let's say you've got a section here in this sample of water. Got air out here. This is defined as y is equal to 0. And you're looking at a section that goes from y1 to y2. This is your sample. So you're going to have 3 forces acting on that. The first is going to be this downward force, and that's going to be due to the water pressure pushing on the top of the surface. In other words, all of this stuff up here pressing down. You've got an upward force that's going to be due to the pressure on the bottom. And then you've also got gravity, which if you put at the center of mass is going to look like this. All 3 of those forces balance out. So if you were going to write how those forces are balanced, F of 2 is going to be equal to F of 1 plus mg, which if you look at the free body diagram here, let's focus on that a little bit more. Force pushing up, F2, is going to be equal to the sum of those 2. So if we're going to take that and we're going to rewrite it with pressures, this is what it's going to end up becoming. Now, how do we get to that? Well, remember that the pressure of 2 is going to be equal to the force divided by the area. So if you're just wanting the force, you multiply both sides by the area, and that's where that term comes from. If you, again, look at this, just multiply both sides by A, and that you get F over here is equal to pressure times the area. Then over here, pressure times the area, and remember that the areas in both of these cases are going to be the same. Plus, now this is going to be interesting, the density times the area times y2 minus y1 times gravity. Where did all of this come from? Well, this is the g's we're not going to compare, but so the rest of this, the density times the area times this dimension, it should be the mass. If we divide through by A, because it's going to be the same all the way through, we find out that the pressure, this pressure 2 is going to be equal to pressure 1 plus the density times gravity times the difference here. For a depth h below the surface in a liquid, this becomes this. In other words, if we take y1, raise it all the way up here to 0, and if we're going down a value of h, then y1, or y2 in this case, I suppose, depending on how it's defined, and that would be h minus 0 or just h. The pressure at a point in a fluid in static equilibrium depends on the depth of that point, but not on any horizontal dimension of the fluid or its container. In other words, remember what we had said at the beginning, that this is going to be a force that's perpendicular to the surface, not anything that's tangential. So the pressure in 14.8 is going to be the absolute pressure. Let's see if we can find it. In other words, this pressure, it consists of P naught, which is the pressure due to the atmosphere, and the additional pressures from the fluid. The difference between absolute pressure and the atmospheric pressure is going to be called the gauge pressure, because we're going to use a gauge to measure this pressure difference. The equation can be turned around to calculate atmospheric pressure at a given height above the ground. So you can see the change there in the sign. Instead of us being submerged in a liquid, we're actually going to be surrounded by air, and we're going to be above the ground. So our pressure is going to decrease. So, checkpoint 1. The figure shows 4 containers of olive oil. Rank them according to the pressure at depth h, greatest first. The answer, of course, is that all the pressures are going to be the same. All that matters is the distance h from the surface to the location of interest, and h happens to be the same in all cases. If we go back and look at our equation here, the pressure is going to be equal to the atmospheric pressure plus the density times the gravity times h, nothing else. Since h is the same in all of these cases, it doesn't matter the shape. So here's a figure, and it's going to be showing mercury barometers. The height difference between the air-mercury surface interface and the top of the mercury level is going to be h. So in other words, the pressure here is going to be equal to the density times gravity times h. Again, shapes here don't really matter. The height of the mercury column is numerically equal to torr pressure only if the barometer is at the place where G has its standard value, 9.8, and the temperature of the mercury is 0 degrees Celsius. So it's pretty cold. Well, cold to me, I live in the South. Anyway, the height difference between the two interfaces, H, is going to be related to the gauge pressure. So the gauge pressure is going to be the pressure that we find minus the atmospheric pressure, or this. Basically, it's taking the equation that we had here, not there, here, subtracting this from both sides. So the gauge pressure can be positive or negative depending on where the pressure is being measured, on whether the pressure being measured is greater or less than atmospheric pressure. So depending on what this is, it may be greater than or less than 0. Figure 14.6 shows an open tube manometer. So you can see the two different levels here, and the H being the difference between the two. You've got it open up here, and then you've got it where you've got a tank that has some kind of fluid in it. Just pushing back. So Pascal's principle is going to be governing the transmission of pressure through an incompressible fluid. So a change in the pressure applied to an enclosed incompressible fluid is transmitted undiminished to every portion of the fluid and to the walls of its container. So consider a cylinder of fluid in figure 14.7. So let us consider this. You've got fluid in here, you've got a piston right here, and you've got a bunch of lead shot that's sitting there on top of it. You've got a point P here, and then you've got Px up here, and then you've got a separation of H, and then you've got the level of pressure down here. So if you increase the external pressure and P at any point, increase this, and P at any point must change. So the change here is going to be the same as the change in the external pressure. This is independent of the height. So Pascal's principle is going to describe the basis for a hydraulic lever. Input and output forces are going to be related by this. It may be a little difficult to kind of see this as you go through, but if you take this A naught and divide A naught to both sides here, you've got F naught over A naught is equal to Fi over Ai. So the pressure of 1 at the beginning, O, is going to be the same as the pressure at the end, I. Watch the difference here between that and the distance of movement. If you'll notice, the distance O and the distance I are the same position as F of O and F of I. Well, watch what happens here. the areas invert. What this means is that a small input of force here produces a large output of force here. However, you're going to have to push a little bit longer distance here in order to generate that large output of force, and that output of force is just going to make a small change in the level. But it can be done. This is the same principle involved whenever you go and see your car being jacked up on a hydraulic jack. It's the same kind of principle here. That's how it's able to lift those heavy cars. So the work done on the input piston equals the work output. Work is going to be force times distance. So FODO is going to be the same as FIDI. If you put in what FO is going to be equal to and what DI is equal to, then you can see where the areas cancel out, and this is what you end up with. So with a hydraulic lever, a given force applied over a given distance can be transformed to a greater force applied over a smaller distance. Okay, if you've ever been in a swimming pool, then you have at least some idea behind the feeling of the buoyant force. And this is going to be the net upward force on a submerged object that's exerted by the fluid in which the object is submerged. So this force opposes the weight of the object, and it comes from the increase in pressure with depth. The further you go down, the greater the depth of the pressure actually becomes. So if you take an object here, you take it out, what you are looking at here is going to be the buoyant force, and that's going to be the pressure from the surrounding water. Now, if you have an object such as stone, where the net force is downward, in other words, the force due to gravity is going to be greater than the buoyant force of the molecules around it trying to push on it, that stone will sink. However, if you have a case here where the force of gravity pulling on this block of wood is less than the buoyant force, the force of the molecules pushing on this, this will go back up. It will float. The stone and piece of wood displace the water that would otherwise occupy that space. So Archimedes' principle states that when a body is fully or partially submerged in a fluid, a buoyant force, or F of B, surrounding fluid acts on the body. The force is directed upwards and has a magnitude equal to the weight of M of F times G of the fluid that has been displaced by the body. So the buoyant force has a magnitude F of B, or F sub B, is the same as M sub F times G. So a block of wood in static equilibrium is going to be floating. And when a body floats in a fluid, the magnitude of the buoyant force on the body is going to be equal to the magnitude of the gravitational force on the body. So the buoyant force is going to be equal to the force of gravity. So when a body floats in a fluid, the magnitude of the gravitational force on the body is equal to the weight of the fluid that has been displaced by the body, which means the force of gravity is going to be equal to the buoyant force, which is what we had defined here. So let's remember that going forward, that when a body is floating, this is true, and this is true. The apparent weight of a body in a fluid is related to the actual weight of the body by the apparent weight is equal to the actual weight minus the buoyant force. So we're going to write this as weight apparent is equal to weight, which should actually be spelled correctly, minus the buoyant force. So, checkpoint 2. A penguin floats first in a fluid of density of P sub 0, then in a fluid of density 0.95 times P sub 0, and then in a fluid of density 1.1 times density of 0, or density at that atmospheric pressure, I should say. Rank the densities according to the magnitude of the buoyant force on the penguin, greatest first. If we're going to look at the magnitude of the buoyant force of the penguin, in each of these cases, the force there is going to be the same. If we're going to rank the densities according to the amount of the fluid displaced by the penguin, then if all of these, if the buoyant force is going to be the same in each one of those cases, which since the penguin is just sitting there floating, same mass, same gravitational constant in each one of those liquids, then the buoyant force is going to be the same all the way across. And the force of gravity is going to be equal to the mass of the fluid times gravity. And remember, the mass of the fluid is the mass that's being displaced. Well, the mass that's being displaced, if we're having a particular density, the mass of the fluid being displaced is going to be more, it has to be more here than in anything else because this is just a little bit less dense. So that mass, or the amount of fluid, is going to be greater here, and followed by 1 times the atmospheric pressure, and then followed by 1.1 times the atmospheric pressure, because this is going to be more dense. And because it's more dense and the force is going to be related to the mass is going to be related to the density. I mean, density is going to be equal to mass over volume. And this one comes in last. Motion of real fluids is complicated and poorly understood. That's good to know. We're going to discuss the motion of an ideal fluid. Laminar flow or steady flow, the velocity of the moving fluid at any fixed point does not change with time. That's about as steady as it gets. Incompressible flow, the ideal fluid density has a constant uniform value. In other words, if it were compressible, you would be able to squeeze the fluid in so that it had a greater density. That you can't do that with an ideal fluid, or that's at least how it's not defined. Non-viscous flow. Viscosity is roughly the resistance to flow, and you can think of it as a fluid analog of friction. The point out of this is that there's no restrictive force here. And an irrotational flow may flow in a circle, but a dust grain suspended in the fluid will not rotate around the center of mass. So, visualize fluid flow by adding a tracer. In other words, you can't see the fluid flow unless you've got something in there that your eyes will detect. So we're going to add that tracer in there. Each bit of the tracer, which you can see here, follows a streamline, much like this. The Streamline is going to be the path a tiny element of fluid was going to follow. Velocity is tangent to the streamline, so they can never intersect. If the velocity of one streamline intersected the velocity of another streamline, it means that one particle would have two velocities, which is not, that's not possible. So the fluid speed depends on cross-sectional area. Because of incompressibility, the volume flow rate through any cross-section must be constant. So the equation of continuity means that the area at 1 times the velocity of 1 is going to be equal to the area at 2 times the velocity of 2. So when a velocity or an area changes, then the other one will change as well. So this holds for any tube of flow whose boundaries consist of streamlines. And fluid elements, of course, as we discussed, cannot cross the streamlines. So if we take a look at this particular diagram, the flow here through this particular larger area, the velocity is described as this. This product of this times this is going to be the same as the product of this times this. The area has become quite a bit smaller. Therefore, you would think that the velocity would be a lot faster. We can rewrite the equation as R sub V is equal to A times V, which is going to be a constant, where R sub V is the volume flow rate of the fluid, or volume passing a point per unit time. If the fluid density is uniform, we can multiply by the density to get the mass flow rate. So R sub M is going to be equal to the density times R sub V, which is going to be the density times A times V, which is going to be a constant. Now, this is a tricky little question. The figure shows a pipe and gives the volume flow rate. In other words, these numbers here are going to be the volume flow rate in centimeters cubed per second, and the direction of flow for all but one section. What is the volume flow rate and the direction of flow for that section? Well, the key to solving this particular problem is to realize, do you have more fluid going in than you have coming out? All of these are going to be considered to be the same area. So all we're really looking at is going to be the flow rate. Well, actually, the flow rate already takes the area into consideration. It's going to be a constant. So, but they all look like they're going to have the same area. So let's take a look at the arrows that are pointing in to this thing. It's going to be, we've got 4 coming in here. We've got 8 coming in here. That's 12. We've got 5 coming in here. So that's 17. We've got another 4 coming in here. So that's 21. So how much do we have going out? We have 2 going out. So that gives us 19. And then we have another 6 going out over here. So that's 13. So our answer here is that the volume flow rate is going to be 13 centimeters cubed per second. And the direction of the flow, obviously, if we've got stuff coming out, it can't just be building up in here anywhere. It's got to go out somewhere, so it goes out here. If it didn't go out, like I said, we would be stuck with material accumulating within this device. So figure 1419 represents a tube through which an ideal fluid flows. We'll come back to this in a minute. If we're going to apply the conservation of energy to the equal volumes of input and output fluid, what we find here is that the pressure of 1 plus 1/2 the density times the volume squared of 1 plus the density times the gravity times the height, y1, is going to be the same as the sum of all of those at point 2. As you might have guessed, this term right here is going to be called the fluid's kinetic energy density. So let's take a look at a zoomed in part of this particular graph. So we've got velocity going through here, we've got pressure here, we've got y sub 1 here, we've got y sub 2 over here, got the velocity 2 here, and this is after a certain amount of time. This is where we started, this is where we ended up. What you're going to see is that these figures right here, we're going to have the same amount on each side. So equivalent to 14.28, which is what we've got here, then we can write one side as a constant, and this is going to be considered another form of Bernoulli's equation. So if we're applying this for a fluid at rest, we find equation 14.7. If we go back to 14.7, applying it at rest, this is what we come up with. Applying this for flow through a horizontal pipe, in other words, y would be equal all the way across. This term drops out and we're just left with the kinetic density energy plus the pressure. If the speed of a fluid element increases as the element travels along a horizontal streamline, the pressure of the fluid must decrease, and conversely, you're dealing with something that is a constant level. If one of these increases, the density is not going to increase. So if the velocity increases, then the pressure must decrease. So checkpoint 4. Water flows smoothly through the pipe as shown in the figure, and it will descend as it goes through. Rank the 4 numbered sections of the pipe according to the volume flow rate through them. If we look at the volume flow rate, volume flow rate is going to be a constant, and it doesn't matter where we are in this. So because of that, all are going to have the same volume flow rate. Doesn't matter where we are. For part B, the flow speed V through all of them as we go from 1 to 2 to 3 to 4. And here's part of the reason why. If we are looking at comparing areas here, this is the smallest area. This is going to be a bigger area, and then finally a much bigger area here. With the smaller area, you're going to have a faster velocity. But as that area increases, you're going to see that pressure start to increase and the velocity is going to decrease. That's why it goes from 1 to 2 to 3 to 4. And finally, as far as the water pressure is going to be a function here of not only the pressure, but the velocity, as well as the height. The reason 4 comes first here is that not only is it the lowest, but it also has the biggest area here, which means that your velocity is going to be small. So if you've already got this being reduced and this being reduced, then the pressure if everything added together is a constant, the pressure must be the greatest. As we go from here on back, we can see here that the velocity speeds up, but we're still at the same level as what we were before. And that's why 3 is less than 4. As we trace back again, this gains height. Because it gains height, this term becomes greater. And as it becomes greater, since it's a constant, that means that this term must become smaller. And then finally, when we get to this point, not only is it high up, but the velocity is also going to be smaller compared to the other values, and that means the pressure there is going to be the least. So there's all the summary of everything that we've gone through. I hope this one was interesting. I found it interesting myself.